You know that feeling when you use a piece of technology and it just clicks? It feels less like a tool you're holding and more like an actual extension of your own body? Well, today we're going to deconstruct that magic. We're going to uncover the secrets behind those interfaces that feel so incredibly natural and then try to build a universal framework for how we're all going to interact with machines in the future. Okay, let's dive right in.
So it really is a fascinating question, right? I mean, why does swiping on your phone feel so perfect, while some ridiculously complicated TV remote just feels wrong? What's that secret ingredient that separates an intuitive design from a piece of tech that just makes you want to tear your hair out? Let's look at a few really brilliant examples to see if we can figure it out.
All right, first up, let's talk about the unsung hero of the kitchen, the +30 button on a microwave. It's just about perfect. And why is that? Well, because it maps directly to a concept we all get instantly. Time is additive. You want more time? You just press it again. There are no menus, no modes, just one simple, repeatable action for a really simple task.
Now, for something a little more advanced, one-pedal driving in an electric car. This feels so incredibly intuitive because it taps into something we've understood our entire lives. Pressure equals force. You press harder to go faster, you ease off to slow down. It's that simple. A single continuous input replaces two totally separate actions, accelerating and braking, because physics is doing the heavy lifting, not your brain.
Or, hey, just think about the gestures on your phone. When you swipe something away, it doesn't just vanish. No, it moves with your finger. It reacts to your speed, your direction. If you do a slow little drag, you might get a peek at what's underneath. But a quick flick, that commits the action. It's this continuous, physics-based feedback that lets you literally feel the interface responding to what you want to do.
And for a super high-stakes example, think about a fighter jet's control stick. The pilot isn't just typing in a command like turn left. No way. They're expressing an intent, a desire, by applying pressure. The flight computer then takes that intent and executes it safely right up to the aircraft's limits. In a system like this, where things are so critical, intuition isn't just a nice-to-have, it's an absolute necessity.
So, a microwave button, an accelerator pedal, a swipe gesture, and a fighter jet's control stick. What could they possibly have in common? Well, it turns out they all follow this single, really powerful design philosophy.
And here it is. It's called one control principle. The whole idea is about getting a ton of expressive power out of a control with very little mental effort. You're not sitting there thinking about switching modes. You're just thinking, I want to do more of that. The control has one obvious physical thing it does, and the context, your speed, your position, your direction, that's what changes the outcome automatically. It's brilliant.
This slide here really gets to the heart of it. The best controls, they're analog and continuous. You can feel the change as you push harder or pull further. But the bad controls, they force you to remember all these invisible rules, like the difference between a tap and a long press, or a double tap that gives you zero immediate feedback. They make you rely on your memory, not your intuition.
Now, to really, truly understand why this principle works so well, we have to stop looking at the machine for a second and start looking at ourselves. See, the best interfaces, they aren't just designed in a vacuum. They're mapped directly to our own biological hardware.
Think about this number, 20 milliseconds. That's how fast your brain can react to a sound. It's this ancient, hardwired alert system that totally bypasses your conscious thought. It's the reason why a sudden sound, like a car horn or a warning beep, gets your attention instantly.
Now compare that to your vision. It's much, much slower. We're talking somewhere around 150 to 250 milliseconds. Vision is fantastic for detailed analysis, for precision, but for time-critical split-second reactions, it's just terrible. And this mismatch, that's a huge fundamental challenge in interface design. If an alert has to be fast, it needs to be heard or felt, not just seen on a screen.
This table here paints the full picture beautifully. You can almost think of it as the user manual for the human body. Every one of our senses has a different speed and is best suited for a totally different kind of task. You've got the fast loops, like hearing and our sense of acceleration. They're built for immediate reaction. And then you have the slower loops, like vision and typing, which are for careful, deliberate thought. So, the crucial point is this. It's a really simple but profound rule of thumb for any designer out there. Fast actions demand physical, intuitive inputs. And exact, precise actions, they're best handled by the slow, deliberate nature of language or pointing. I mean, you wouldn't fly a plane by typing commands, and you wouldn't write an email with a bunch of gestures, right?
Okay, so we've got the core principle and we understand our own biological hardware. Now we can finally put it all together. We can create a unified blueprint for pretty much any generic interface, whether it's a creative tool, a vehicle, or even an AI assistant.
This blueprint is built around our own reaction loops, mapped directly onto a timeline. You see, the fastest layer, at basically 0 milliseconds, that's for our subconscious reflexes. The stuff that keeps us safe. Then come the alerts, which use our super fast hearing. After that is the loop for continuous physical control. And only then, in the slower domains, do we use vision for confirmation and language for long-term planning. Good design has to respect this natural order.
So here's the control stack itself. Let's go back to that fighter jet example. Layer 1 is the pilot's physical intent, pushing the stick. Layer 2 is the immediate feedback, like the stick vibrating to let them know the plane is at its limit. Layer 3 is spatial awareness, the heads-up display showing the horizon. Layer 4 is for precision, like targeting a specific point on a screen. And finally, Layer 5 is for abstraction, using your voice to say, plot a course home. See how each layer builds on the one before it, going from fastest to slowest?
So why does any of this matter? Well, because our systems are getting more and more complex, more autonomous, and our methods of controlling them just have to evolve. So let's apply this blueprint to a really futuristic scenario, managing a swarm of 100 autonomous agents all at once.
The key shift is this. You are no longer a direct operator. You're not micromanaging. You're an orchestrator. You don't tell agent number 47 to slow down. Instead, you create and you shape these intent fields. Maybe you adjust a risk gradient over here or a speed envelope over there. You're basically conducting an orchestra, not trying to play every single instrument yourself.
And how does a system like that get your attention without totally overwhelming you? Well, it uses an escalation ladder. The default state, when everything's going great, is just silence. If a trend starts to deviate a little, you might hear a subtle shift in an ambient tone. If one specific agent has a problem, a directional sound will point you right to it. A haptic pulse to your body might ask for a quick glance. The system has to earn the right to interrupt you.
This is where eye tracking becomes pure magic. But there's a non-negotiable rule. Looking is for targeting, not for commanding. Your gaze is the fastest way to route your attention to an agent that's in trouble. But the actual action, that always requires a second channel. A hand motion, a change in pressure, a voice command. This is what prevents accidental actions, and it feels completely natural.
So what kind of hardware do we need to actually build this thing? Well, it's a surprisingly minimal stack of stuff. You've got a microphone for high-level commands, eye trackers for attention, a pressure-sensing stick for physical intent, and body haptics for feedback. Each piece maps directly to one of the layers in our stack. And the most exciting part about this? This isn't science fiction. All of these components exist right now.
And ultimately, this is the big takeaway. We need to stop thinking about interfaces as just screens filled with buttons and menus. The perfect interface isn't something you look at. It's something you feel. It's a direct, continuous, and totally intuitive conversation between your nervous system and the machine. So what happens when our tools finally learn to speak our body's native language?